Hello and welcome back to the second part of Chapter 6. Today we're going to talk about hypothesis testing, how you go about developing a null and alternative hypothesis, some things to avoid like type 1 and type 2 errors, hypothesis test of the population mean, a hypothesis test of a population proportion. So it's following the same outline as we've done for the last couple of chapters. We're going to show you examples of mean and proportion and how you do testing for that today. So the first thing we'll talk about is the null hypothesis. And the null hypothesis is typically something you want to prove wrong. That is, you want to state it in such a way that your results will refute what that is. And so what we're really after, though, is then the alternative hypothesis. And that is typically going to be opposite of what you're saying is the null hypothesis. And what we will do then is use data from a sample to test how valid the two statements are. So it might be, I believe there's going to be, an increase in the test scores for this next test. And the way you say that is okay, the alternative hypothesis would be the average will be equal to 92. The null hypothesis, the average will not be equal to 92, or vice versa, depending on what you're trying to prove. So some things you need to be aware of is you need to think about the situation of your area of what the hypothesis is going to include. And the way we prove or disprove that hypothesis test is to collect a random sample. Because the idea is that we won't be able to sample the entire population, so we want to collect a sample that's representative of the population. And we saw from chapter 5 that if we keep repeating a random sample, then the average or mean of whatever we're collecting of those random samples should approach the actual population mean. So we have some idea or some confidence, if you will, that our random sample is going to be representative of the population, and that we can generalize from the results of that random sample to the population. And so, like I was saying at the beginning of this lecture, it's when you think about these hypotheses, what you want to do is it's best to begin with the alternative hypothesis and make it the conclusion that you hope to support. So the null hypothesis, or the null hypothesis, is going to be the opposite of your alternative hypothesis. And those hypotheses don't always have to be about research, but you typically would begin with a statement about the value of the population parameter that you think is true. So my example, I think that the average of the next test will be equal to 92. So then you need a hypothesis test to challenge that, determine whether there's statistical evidence to conclude that that conjecture is incorrect. So if I get a random sample and the sample gives me an average be 93, is that different from my 92? And I need to show that it's significantly different. Now, where did I get those averages? So they might be averages from last year. Maybe I've taken I'm teaching the same class, using the same book, same tests, and then over the last 2 or 3 years, I see that average for that next test is usually this amount, whatever amount I'm looking at. So as you work through these two tests, again, you have something in mind that you want to prove. That's typically going to be your alternative hypothesis. So then you'll develop your null hypothesis from that. You typically would write that down first. And so the alternative hypothesis then would be something that you believe is not what you've stated in the null hypothesis. Okay, so when you're looking at these different hypotheses, you can either do a one-tail test or a two-tail test. When you use inequalities of whatever you're looking for, that's going to be a one-tail test. The third form here is going to be a two-tail test. So how do you know which hypothesis is which? Null typically means starting with 0. So H sub 0 or H null or the null hypothesis is written this way. And then the alternative hypothesis has a subscript of A. So you would know that. So these two, see if I can draw on the screen here, are your one-tail tests, and this is a two-tail test, right? We either say that the population mean is equal to the sample mean, or it's not equal to, but we don't know in which direction that is. And since we don't know what's direction, it could be on either end of the tail. And when I say tail, this kind of goes back to what we've been looking at all along. If we look at a normal distribution of our parameter, so we're saying, okay, where does our mean lie? And where does the actual mean? So let's say the actual mean is here, and we believe that that's going to be greater than whatever we've sampled. So it might be down in this area. Or it's less than. In that case, it's down in this area. And vice versa for this one. Just remember that when you're using inequalities, right, it's not equal sign, then it's a two-tailed test. Otherwise, I'm sorry, I got that misstated. It's a one-tailed test. Then if it's equal to, it's the two-tailed test, because you don't know which one is going to be greater or less than. Hope that makes sense. All right, the next thing we want to cover, and this should be a review for you, is some different types of errors and what we're trying to avoid. So there are type 1 errors and type 2 errors. The type 1 error is right here. That is, we know the null hypothesis is true and we reject it. So we reject the null hypothesis thinking that the alternative hypothesis is true. It's type 1 error. We want to try and avoid that. And that's how most statistical tests are set up for. The other type is the type 2 error. The type 2 error means that we've select conclusion is that we've gone with HO when it's false. So we've accepted HO, but we should have rejected it. So we've accepted the null hypothesis, but we should have rejected it. That's a type 2 error. Type 1 error is we reject the null hypothesis when it's true. So think about that. write it down, get it in your mind so that when you see it on a test or somebody asks you about type 1, type 2 errors, you'll know which way to go with that. So putting that more for you to remember. So if we look at that, if the null hypothesis is true, the conclusion is correct. If the alternative is true, we made a type 2 error if we accepted the null hypothesis. In the second row, if HO is true, we made a type 1 error if we rejected HO or the null hypothesis. So to be correct then, if the alternative hypothesis is true and we reject the null hypothesis, then we've made the correct decision and we've avoided the type 1 error. So again, I would just concentrate on this. We reject the null when it should have been true. That's type 1 error. We don't reject null when we should have rejected it. That's a type 2 error. I prefer to remember the type 1 error. We reject null when we shouldn't. So we want to try and keep this type 1 error to the smallest possibility that we can. That possibility that I'm talking about is called the level of significance. And the level of significance is the probability of making a type 1 error when the null hypothesis is true as an equality. So like I said before, then when you're doing these hypothesis tests, you want to specify the level of significance and the probability of making a type 1 error. So if we look at our significance level at, say, 5%, then we have a 5% chance of making a type 1 error. So that means we're 95% confident then we're making the correct choice between our null hypothesis and our alternative hypothesis. If you're only controlling for type 1 error, then these are called significant tests. So if you get asked what is a significant test, it means you're controlling for type 1 error. So as I said earlier, most types of hypothesis testing control for the probability of making type 1 error. They don't typically control for the probability of making a type 2 error. So when we do the hypothesis test of a population mean, the one-tailed tests are either greater than or less than, or less than or greater than, as you see here. So what you'll do is you'll develop your hypothesis test first, the null and the alternative. Then you'll specify a level of significance for the test. Then you collect your sample data and compute the value of what you're looking at. And this is called your test statistic. So I've drawn a little graph again here, and I'm just looking at the upper tail. So I've got the null hypothesis is that the sample mean is greater than or equal to the mean. So if I have the mean here and I have mu sub O here, then as we can see here, let's say this is 90, this is 92. Let's say the sample mean was right in here. So you can see here 92 is greater than 90, right? We think that's going to be, so the upper tail. Just the opposite if you go for the lower tail. So if we use the example that's on page 255 in your book, we're looking at a coffee study. to determine how many pounds of coffee are going into a can of coffee from Hilltop Coffee. And we believe, or they're actually saying, that the actual value of that coffee is 3 pounds. So the alternative hypothesis would be that we believe the mean is less than 3 pounds. Okay, so it's going to be right in here somewhere, below this mean. So the null hypothesis is that the mean is greater than or equal to 3. So we believe that the null hypothesis that it's going to be in this area, where if you're selling cans of coffee, that's a good thing. That is, you're not defrauding your customer because you're giving them at least 3 pounds. But also, if it's a lot more than 3 pounds, you're not getting paid for the extra coffee that you're selling, and that's not a good thing either. So if you'll recall from earlier in the chapter, we wanted to create a t distribution. And from that t distribution, we can calculate a t statistic. And what we want to do is we want to find out statistically whether it is a significant difference between what we think the mean is and what the actual mean is. And so if you want to, you may want to go back and look at this slide. And so we've got a standard normal distribution and a t distribution with so many degrees of freedom. So that's a little broader than your standard normal distribution. So that if you'll notice the black lines there. So that it allows for some more variability. But that's what we're looking at here is that t distribution. So looking at that lower tail probability for t equals -3, right, from a t distribution with 35 degrees of freedom, we calculate that out at 0.0025. The 35 degrees of freedom came from us doing a sample of 36 cans of coffee. So n-1 is your degrees of freedom. So that's where the 35 came from. So that test statistic for hypothesis test about a population mean is this one. So that t. So if we know our mean minus our estimated, and then our variance divided by the square root of n, all divided into this numerator, that gives us our t value. And if our t value is less than our alpha value, then we are statistically correct in saying that the null hypothesis can be rejected. So I've already given you the answer to this, but the key question then for a lower tail t-test is how small must the test statistic t be before we choose to reject the null hypothesis? And that's where this p-value comes in. It's the probability, assuming that HO is true, of obtaining a random sample of size n that results in a test statistic at least as extreme as the one observed in our current sample. So what's the probability of actually getting the value we got? So what I've got here on the screen is a way to show you how to solve this problem and tell whether what you've got is statistically significant or not, so you can reject the null hypothesis. So let me bring that up. So what I've got here, hopefully you can see it, is what's our sample size. So we're actually counting down through here through, well, row 37, and we know we've got a title at the top, so there are, if we just count that, then there's 36 observations. We get the mean by taking the average function. We get the standard deviation. Notice we're using that S because we're using a sample. And we hypothesize that it's going to be 3 pounds in each of the cans. Okay. And so I just copied the values off to the side here that Excel returns, and I'm showing you the actual formulas. So then what we want is the standard error, right? So that would be this value divided by the square root of this value. Okay. Our test statistic then is going to be this value minus this value, so that's the average, minus what we hypothesized, divided by the standard error here. And that gives us this t. The degrees of freedom is going to be our count, this value, minus 1. So then we can use a function called t distribution that takes 3 parameters. Right? So the first parameter is going to be your test statistic. The second parameter is your degrees of freedom. And the third parameter is the value if you want just a single value or if it needs to be cumulative. This returns the p-value for the lower tail, which is this amount. If we want to know what the p-value for the upper tail is, we just subtract this amount from 1, which gives us this. Then if we wanted to do a p-value for a two-tailed test, we would take 2 times the minimum of either this value or this value, right? Which is going to be this. So again, if we're drawing this out on a distribution, so this is saying, okay, this is 0.00389, which is this value right here. And this value becomes right here. That's the upper tail test. But since this is the smaller of the numbers, if we're doing a two-tail test, what we're doing is just adding whatever proportion is underneath here, which is 2 times the minimum one, which is this. So that becomes our p-value for a two-tail test. So that's what they're showing you in the book here. All right, so then they graphically show you that as well. And so the sample mean that we got is 2.292 with a standard deviation of 0.17. Right, so they show you how to calculate that t statistic. And then how to get that p-value. So that p-value is exactly what we just showed you here. So the probability of getting that t statistic. So what you got to remember, what I said from about 3 or 4 slides ago, is then if you have the p-value and you know your level of significance, if your p-value is less than or equal to your alpha, then you can reject the null hypothesis. So let's say our alpha, we wanted to be sure that we didn't sure that we didn't have a type 1 error of, say, for 5%. So as long as our p-value is less than 0.05, we can reject that null hypothesis if it's different. If it weren't different, our p-value would be much higher than alpha, and we couldn't say that our null hypothesis was different than what we were testing for. In this case, what we're testing for is 2.92 equal to or greater than or equal to or less than or equal to our 3 pounds that we think they are selling in their coffee cans. So this is our null hypothesis, that the mean will be equal to 3. So we've collected sample data. We saw the sample mean was 2.92. So our alternative hypothesis is we believe they're selling less, so H sub A is mu is less than 3. Can we, what we're always testing for, is can we reject the null hypothesis? And in our case, we saw that our p-value of 0.00389 is less than our level of significance, which is 0.05. Then we can reject that. Now, since it's a one-tailed test, our 0.05 would be divided in 2, and that'd be 0.025. So for a one-tailed test, if our p-value is less than or equal to 0.025, we can say that it's less than, right? We can reject that null hypothesis. If we flip that around, then for an upper tail t-test, the p-value is the probability of attaining a value for the t-statistic as large or larger than provided by the sample. Right? So, in summary, then, computation for p-values, you want to compute the value of the test statistic using the equation 6.11. And 6.11 is found on page 256. For the lower tail t-test, using the t-distribution, you compute the probability that t is less than or equal to the value of the test statistic. For upper tail t-test, using the t-distribution, compute the probability that t is greater than or equal to the value of the test statistics. So now we'll run through when you want to do a two-tailed test about the population mean. Either your sample is equal to your mean, your sample mean is equal to the mean, or it's not equal to the mean. You don't know in which direction. So you don't know if it's lower or if it's upper, you just know that you think it's going to be different. So here we have an example in the book where we are producing units for retail outlets, and we think they're going to order 40 units per retail outlet. This is for the holidays, holiday toys. So we want to know how confident are we think it's going to be 40, or do we think it's going to be less than 40? And coming up with these hypotheses will help us determine our production, whether we're going to provide that 40 or not, or should we increase our production. So here I've got the orders file on the screen that you can look at and see how they solved it. And you could just run through this yourself. Again, we're calculating the sample size. Since these are numbers, we can use count. We calculate the mean. We calculate the standard deviation of a sample. So stdv.s. What we think is going to be 40. We can calculate our standard error, our test statistic, degrees of freedom, because we collected 25, so it's n minus 1. And we go through and we calculate the lower tail, the upper tail, and then what that for a two-tailed test. So in our case, the two-tailed test is 0.28. So is that lower than 0.05? It's not, so we can't reject the null hypothesis. So I'd urge you to open this up, see what those functions are, and maybe run through and see if you can do the same thing in your calculations. So what I just showed you as an actual spreadsheet is what you see, what you just saw. And so again, look at that, pay attention to what they're doing in your book. It's a fairly straightforward process of what they're doing. All you got to remember is the p-value has to be less than alpha. If that's the case, you can reject your null and accept the alternative hypothesis. Remember, we're always trying to avoid or minimize the type 1 error, so that's what we're testing for, to avoid that. So then the process here is you compute the value of your test statistic using that equation. If the value of the test statistic is an upper tail, compute the probability that t is greater than or equal to the value of the test statistic. If the value of the test statistic is in the lower tail, compute the probability that t is less than or equal to the value of that test statistic. Double that probability of one of the tails, the minimum number, to get the p-value. So then the calculations are as follow, whether you're doing a lower tail or an upper tail or a two-tail test. And so you're just doing these calculations. So I'm going to pause right here, and when we come back, we'll come back and review these steps for hypothesis testing again.